Hi, everybody. So today I wanted to talk a little bit more about this theorem that we ended with in Friday's video, um, which says basically exactly what all the surfaces um, that we can get by gluing edges of polygons together look like. And, at first, when we started doing this process of taking a polygon and identifying edges, you might have thought, oh, it's impossible to figure out, what all the possible surfaces are that we can get this way because, you can choose a polygon with 8 trillion sides and you can identify the edges in all sorts of different ways. And so what hope is there of sort of classifying them in any reasonable way? And so because of that, this theorem is kind of remarkable. Really, there's sort of two classes of surfaces. There are one type, which is taking a torus and connected summing it with another torus and doing that, as many times as you want to get something that looks like some sort of pastry with many holes. And that's one class of surfaces you can get. And then the other is doing the same thing, but with projective planes instead of the tori. And that's harder to draw, of course. And we've already seen that the Klein bottle, which doesn't immediately fit into one of these two categories, it turns out that this is equal to connected sum of two copies of the real projective plane. So that gives us hope that a theorem like this might be true. Okay. But once you have this theorem, how might you go about proving it? At first it seems difficult, but what we're going to try to do is start with some sort of arbitrary polygon with edges identified, and through some sequence of steps show that we can change it to something that's a little bit simpler. And what do I mean by that? Well, we have to think about what the connected sum looks like. This hash symbol. Remember, in terms of polygons, if I have two polygons, with some sort of edge identifications, I'm not really going to specify what they are. So that's one, and here's some other edge identifications. Remember that the connected sum basically means I just take a larger polygon whose edges are all of the blue edges and all of the purple edges. So I just kind of glue the two polygons together by choosing a vertex of each and stretching it out and gluing them along that new edge I've created to get a polygon that has the edges of the two I started with. Okay. And so for instance, as an example, let's say I have a surface, I'll call it X, and I'm going to describe it as some big polygon. I'll just draw that. That means some polygon with hundreds of edges and edge identifications, which I'm not going to specify. And we know that RP2 can be represented as a lune. So just two edges glued together with a twist. Maybe I'll draw some edge identifications here. Something complicated. So X is complicated. RP2, I know exactly what it looks like. Well then, if I take the connected sum of X with RP2, what I get is my big complicated polygon. Actually, I have to choose a vertex to spread out, right, on each of these. So maybe I'll make that more clear. So I have my big complicated polygon on the left, and on the right, I just spread out those two edges, and it looks like that. Okay. And so x is complicated, RP2 is simple. The connected sum of x and RP2 has a complicated part and a simple part. And kind of using the reverse logic of this, so on the other hand, I can go the other way. Whenever I see a picture like this, I know that a piece of it had to be RP2. Whenever I see a polygon with edge identifications, that looks like the following. So something complicated, I don't care what it is. And then it's got two edges which are adjacent to each other. So two adjacent edges. Glued with a twist. If I see this, I know that it has to be the connected sum of the blue part with an RP2. So this is topologically equivalent to, we're always talking about topological equivalence here. So when I say the same as, I mean up to some stretching. This is topologically equivalent to a connected sum of the blue part connected sum with this thing, which is just RP2. Okay, and so if I'm trying to prove this theorem here, showing that any one of these polygons is one of these two forms, this is how I might take something that's complicated and reduce it to something slightly simpler. I had this polygon, this big one here, and I was able to argue or reason that it's the connected sum of a single RP2 with something a little simpler. And why is this simpler? Well, it has two less edges than this one did. So I've reduced my problem. And so the goal is to come up with a series of reductions of this form that allow me to take any very complicated polygon with edge identifications, many sides with complicated gluing, and gradually remove pieces until I can show that what I had, all the pieces were of these forms. Either a bunch of copies of the tori or a bunch of copies of RP2, all connected sum together. Okay, so let's look at something slightly more complicated. Actually, before I do that, let me talk about the torus case. If I have a big complicated polygon like this, but I see in this polygon, I see four adjacent edges that have this kind of gluing, then similar to before, I can say, well, this is just the complicated part connected sum with something simpler, which is the torus. Because if I start with this on the bottom and I do the connected sum, I get exactly that. Okay, so I can also see tori inside this polygon as well, and I can always pop a torus off and reduce my problem to something with fewer edges. Okay. Now let's do something a little harder. So what if I don't see anything like either of these two pictures? I mean, these are very special pictures because these edges here are adjacent to one another, and as are these four edges. They're all, one after the other. But in general, if you have a general polygon, you might have a bunch of edges, So, you might see something that looks like an RP2 in the sense that I see two edges being glued together with a twist, but they may not be adjacent to each other, right? And so if that's the case, how do I deal with this? Well, remember we have sort of one main tool at our disposal, which is that we can always cut our polygons and remember that we made the cut, so create an edge identification. But that allows us to represent these surfaces in different ways. So, for instance here, I can cut this, and then I have two pieces. I have a left side and a right side, and I can rearrange these by gluing the red arrows together. And I haven't actually changed my surface as long as I remember that this purple cut I made is actually a single edge. So I have to draw an arrow to remember that gluing. And so if I do that, if I take these left and right pieces, split them up, and glue along the red arrow, what do I get? Well, let me just copy this. So here's the left side here. And it's got this purple edge still. And then the right side, if I want to glue the right side onto the left side along the red arrow, I'm going to have to flip it over so that the arrows are pointing in the same direction. And so what that ends up looking like is the right side here. Well, where's the purple arrow go? So on the right side, the purple arrow is coming out of this red arrow. So it's coming out like that. And then between the back of the red arrow and the front of the purple arrow, there's just a bunch of complicated stuff. Okay, and so in doing this, I haven't actually changed my surface. I've just represented it in a different way because I've identified these two sides, which shows, is pointing out the fact that secretly they're the same side of my surface. Okay, now let me, we only care about topological equivalence here, so I can stretch this. Maybe I'll do a squiggle for topological equivalence. And so if I stretch it a little bit, I'll just draw these purple arrows like that. And then again, I still don't know what's going on with the rest of the polygon. It's something complicated. Okay, but now here we see that we have something complicated, but now we have these two pieces which come from an RP2, and they're adjacent. In fact, I designed them to be adjacent. And so what we get here then is something that I don't know, the blue part, connected sum with RP2. Okay, and what does this tell us? It tells you that anytime you start with a picture like this, so the conclusion. You know, given some polygon with edge identifications, or let me rephrase this slightly. Given a surface X, which is given to you represented in this way, represented as a polygon with edge identifications. So if I'm given that, if I can so basically if I see a picture like this, and what do I mean by a picture like this? I mean if I see two edges anywhere on the polygon, which are supposed to be glued to one another with a twist, I can, you know, via some cutting and gluing, I can represent this polygon as something more familiar, which is a complicated part together with two adjacent edges glued together with a twist. And what that gives me is some x prime, a new surface, connected some with RP2, where here, just like before, the x prime is the complicated part, and the RP2 is these two adjacent edges glued together with a twist. Okay, and so let me summarize it just one more time. You know, if I'm given some complicated polygon, or if you are on an exam, and you're asked, you know, in terms of the theorem, like what surface does this represent? You know, is it one of these? Is it one of these? The way to go about figuring this out is to try to simplify it into pieces. And here's one move that you can do. One move you can do. If you see two edges that are glued together with a twist, then via this cutting and gluing procedure, you can re-represent that surface as a new surface where you've got two edges that are adjacent to each other glued with a twist. And whenever you see that, you know that part of your surface was an RP2. Okay. So let me give you an exercise. Which is the following. Kind of similar to what we just did, but with a torus. So, given a polygon with edge identifications, if you can find edges glued like this, so like a torus. So if you can find two edges that are glued, so two edges that are glued without a twist, and two other edges that are glued without a twist, like that. But let's say they're not adjacent to each other. So there's a bunch of other edges in between these ones. So a lot of complicated stuff is happening in between. Still, you might kind of hope that there's a torus in this surface, in the sense that this surface can be represented as something connected some with a torus. So that's the exercise. Show that that's the case. Show that via a sequence of cuts and glues but never changing the surface. So you always remember where you cut and draw arrows on those new lines to show that they're identified. That you can represent this surface as the following. Bunch of complicated stuff. But four edges, and these new edges are going to come from the edges that you created by cutting and gluing. Well, by cutting, I guess. Four edges like this that look like a torus. And now they're adjacent. And so we can say that this is equal to the part that we don't know, connected some with something we are familiar with, which is a torus. Okay, so that's an exercise. See if you can work it out. It's actually significantly harder than the case of RP2, but if you play around with it for long enough, you can probably figure it out. It requires, let me see, I think it requires cutting and gluing 2 times. So one cut's not going to be enough to solve the problem. But once you have this, you can sort of see how the strategy of proving this theorem is going to go. Basically, you start with some arbitrary polygon with arbitrary edge identifications, and you look for toruses and RP2s within that. You look for 2 edges like this, 2 edges that are glued with a twist, and then through a sequence of moves you can replace that with 2 adjacent edges that are glued with a twist. Then you know that that's an RP2. And so you can rewrite your surface X as some X prime connected some with RP2. And basically, do that until you can't anymore. So do that until you can no longer find any edges glued together with a twist. And then see if you can find toruses inside your surface. So whatever the remaining part is, look for this kind of picture, where you've got 2 pairs of edges that are glued with no twists. And whenever you see that, there's a sequence of moves that replaces that surface with one where you've got those edges, the same kind of picture, but they're all adjacent to each other. And then you can break off a torus. And the hope is that you do that enough and you're left with no more edges, and then you can go back and see what you have. So I'm going to get into the details of this a little more carefully in the next lecture. But for now, just think about that exercise, and then we'll talk about it more on Wednesday.